Alright, so today I'm going to be explaining another important paper with the title Flexible Diffusion for Graph Neural Networks. This ICLR paper in 2024 is very important. Graph neural networks are attracting growing attention due to their promising performance in modeling a variety of graph structured data. However, most existing GNNs only consider fixed range, discrete message passing and aggregation. None of them are aware of the importance of the degree and local structure of nodes for smoothing features, which significantly limits the applicability of GNNs. So, previous approaches either focus on adaptive selection for aggregation structure or treat discrete graph convolution as a continuous diffusion process, lacking holistic consideration of the two issues and resulting in the performance of the model being significantly limited. So we propose a novel flexible diffusion convolution called FlexiDC, which aims to smooth features by setting a specific continuous diffusion for each node through the degree and local structure of node. Specifically, it first extracts the degree and local structure knowledge of the nodes in the graph data and then injects it into the diffusion convolution module to smooth features. So we have a message passing neural network with this aggregation and update equation. Now, first you should know what is a graph diffusion convolution. GNN typically rely on discrete feature aggregation and propagation operations to update node information. But recently, researchers have focused on extending this discrete operation to continuous graph diffusion. The key is that the propagation mechanism of graph diffusion convolution addresses this problem in the following way. So H hat is the hidden feature matrix, and when T is to the K is the case order polynomial in the Laplacian matrix, which depends on nodes within a maximum distance of K steps from the target node. It is worth noting that the summation from 0 to infinity, because the kth power, but kth power can be any number from 0 to infinity. So it means that each node aggregates information from the entire graph. So equation 2, T is a generalized transfer matrix which is equal to A hat. And these parameters theta k, their sum should be equal to 1. For example, two of most commonly used diffusion weight coefficients, when theta is this one, you will see this is about this paper. When theta is this one is personalized page rank. So any particular case of theta, you will have a different popular method. So this is the overall architecture of flexible diffusion convolution, which consists of degree-based flexible diffusion and label smoothing. K refers to K-hopping neighbor structure. The leftmost part represents the input of the model, which can be either a homophily or heterophily. The middle part involves degree-based neighborhood diffusion, which smooths the features and feeds them into an MLP for further processing. Finally, the output is fed into rightmost part for label smoothing. So the inspiration behind it is that in graph data, the degree of nodes varies greatly. If we use the same size of local structure, same receptive field for each node in previous GNNs, larger local structures may lead to over-smoothing, while smaller ones may result in instability and insufficient information aggregation, making it difficult to achieve the optimal vector representation for all nodes. Additionally, because the adjacency matrix is discrete, the local structure is also discrete, making it impossible to describe the continuous relationship between nodes. This limits the information propagation between nodes and may result in the information loss or inaccuracies. By designing reasonable aggregation local structure sizes based on node degree information and using diffusion kernels to reach a continuously changing neighbor radius, the representation of nodes can be made continuous, thereby improving the model's applicability and generalization ability. So if there exists a significant variation in the number of neighbor nodes, which is referred to as the difference in node degrees. If the traditional GNNs aggregate only the immediate neighbors for message passing, the nodes with higher degrees receive too much information, causing over-smoothing, whereas the nodes with lower degrees may not have enough information for self-enhancement. To address these shortcomings, they propose a method to calculate appropriate aggregation range based on the degree of each node. And the goal is to match the local structure aggregated by each node with the number of its neighbor. So in order to take into account the global information of graph in the model, combining a spectral and spatial GNN is proposed to improve the predictive power. In the spectral GNNs, the graph data is viewed as a discrete signal can be transferred into frequency domain by Fourier transform. And the Chebyshev k-order truncation is used here to approximate the convolution kernel. And here S prime, this S prime you see here, is the resulted modulated signal. Following the principle of classical physics, taking the formal form, this form utilizes to describe the diffusion of heat and other substances within a continuous medium. The diffusion equation employed within graph neural networks is like this. And the presentation on diffusion is in the appendix of this paper, appendix A of this paper. To put it succinctly, we can achieve the flexible diffusion convolution by extending feature propagation function present here to each layer. So we extend this feature propagation function, and now what is continuity training? The diffusion convolution allows us to use continuous kernel functions in place of discrete feature aggregation functions. To prevent overfitting of the model, we propose a bi-level optimization. This is a bi-level optimization. Many problems in machine learning can be represented as a bi-level optimization, like training and validation, or any other cases. We first train the model weights on the training set and then find the optimal kernel radius based on the minimum loss on the validation set. Yeah, this is the idea that I said, training and validation, that they used here. I've seen that in different papers as well. So because they formulate it as a bi-level optimization problem, which is very important in everywhere, especially in game theory. And label smoothing. For training GNNs, most existing work focuses on minimizing the expected cross entropy loss between ground truth targets and a prediction of the model. So minimizing the loss is equivalent to maximizing the expected likelihood of labels selected according to distribution T of C condition on I. For example, using hard targets ignores the correlation between connected nodes. To overcome the overconfidence issue mentioned above, label smoothing has been proposed to find a distribution. So the method for smoothing label is defined like this. And K sub I follows the definition of equation H. And then they talk about sensitivity. And these are the classification accuracy or ablation studies for two submodules.